Hi everybody, this is Robert Hodges, and I'd like to welcome you to my talk today, SQL Row Store versus Data Warehouse, which is right for your application. It's a pleasure today to be presenting at Percona Live Online 2020. Before I dive into the talk, I'd like to just say up front, thank you so much to everybody at Percona who's helped to put this together, and thank you all in the audience for joining us. It's always a pleasure to present. With that, I'd like to dive into the talk. Just a little bit about me. My name is Robert Hodges. I'm Altinity's CEO. I've worked on databases since 1983, so it's been about a 30-year run on databases, which also leaves out a couple of detours into things like virtualization and security. Of the databases I've worked in, ClickHouse is database number 20, and one of the ones that I've enjoyed the most. Other databases that I've worked in extensively include MySQL and Sybase. A little bit about my company, Altinity. We style ourselves as the enterprise guide to ClickHouse, so we basically make enterprises successful at designing and operating analytic systems based on ClickHouse. We're a major committer to the ClickHouse open source project, as well as a community sponsor in the US and Western Europe. Let's get to the meat of the talk. So, the idea of this talk was to contrast row and column stores and to give you some guidelines about when each one is appropriate. So I'm going to start this by just talking a little bit about what do we mean by a row store and what are the salient characteristics. And as my row store, I'm going to use MySQL as an example. So I'm going to, first of all, start by just reviewing some key features of MySQL. And one thing about this talk, I'm assuming you've seen MySQL before, you have some familiarity with it. And so what we'll do then is we'll be able to contrast this with the data warehouse and see how they're different. So let's look at MySQL. First of all, it's really simple. Single C++ binary. You fire it up and you have a running database. It talks SQL. It uses what's called row storage, which means that the data are stored in tables and then organized by rows in storage. We'll look more deeply at what that actually means. This picture over here gives you an indication those red triangles are meant to be indexes. MySQL is very good at supporting high concurrency. In other words, you can have thousands of clients simultaneously logging into MySQL and doing quick transactions and moving through. One of the ways that it does this is that the queries are 99% single-threaded, which means that when you connect to the SQL server and do something, there's a single thread doing it for you. There's no real effort to parallelize within the connection. MySQL also has a single server model. Of course, you can have replicas using MySQL replication, but the basic idea is the scope of a query is a single MySQL server. If you want to span queries, you're going to have to add extra software on top to do it. And then finally, MySQL is open source. So it's a GPL v2 license, which means that you can use it for just about any purpose you want. The only place where you get restrictions are if you want to bundle it with binaries that you ship to people. So these are overall characteristics of MySQL, and I would guess that most people on this call know this. Let's look in detail about what that actually means when you design applications. So I have a little sample app here which involves airline flight management. It's actually using some data that we use as a pet data set. It's the on-time data from the US government that tracks flights of commercial aircraft. And when we take a system like this that's tracking airline flights and map it to MySQL, what we'll typically do is break it up into a set of related tables. So the core table in this system is called OnTime, and it has a row for every leg of a commercial airline flight. So for example, if I go from Oakland to Denver, there's going to be a record in there. And if my plane then flies from Denver to Chicago, there'll be another record. So that's the table in the middle. You have flight date, carrier ID, other data. The things with underlines are actually foreign keys. They point to other tables. So for example, because I might want to manipulate dates in different ways, I've got a time table which breaks out time in different ways, like the date by year, by quarter, by month. This is a common way to do analytic, to organize analytic data. We also have tables to look up our carrier and our airport. And what that means is the on-time table can be made narrower because it doesn't contain this extra information about, for example, the airport, such as its latitude and longitude. And this is a common practice. It's called third normal form and is a standard way to lay out tables in MySQL. Let's go ahead and dig a little bit more deeply into what's going on under the covers when we set up this table. So if we go into InnoDB, what we're essentially going to see is three major types of structures. There's going to be the table itself, the table data, which is stored by rows. But within InnoDB, actually the rows in this flight table are actually stored as leaf, sort of the leaf of a B-tree index, which is a B-tree index, which is uses the primary key of the table. So, for example, in InnoDB table, there's generally an ID column, which is usually an integer of some kind that allows you to get to the record quickly. And InnoDB then structures the data so that it is ordered in order of these IDs. And the clustered index allows you to find any individual record using its primary key. So this is a very efficient structure, but the two things to notice are the data are stored by rows. So if you read part of a row, you end up generally reading the whole thing at once. And also, the data are going to be ordered by your IDs. So whatever ordering they have, that's how the rows are going to be arranged. The third structure is called secondary indexes. And one of the things about row databases is they don't like to do table scans. So if you're around SQL, you hear, oh, it's now doing a table scan. That's usually something bad that you try to avoid. And instead, what you'll do is create indexes which can then find other values allow you to jump to specific rows that have values that you're looking for. So for example, I have an index here on flight date, which allows me to find things by date. I have an index by carrier ID, which allows me to find the flights for a particular carrier. So this is the underlying structure that we have. And it has some consequences that as we look at different types of applications, the structure is good for some and bad for others. So with MySQL, what's kind of interesting is that it's really focused on a type of processing that we call OLTP, or online transaction processing. These types of applications have lots of lookups, so going and looking at individual rows or small numbers of them, lots of updates to those rows. They often have relatively high concurrency, so a lot of clients simultaneously doing this, and there are often applications where you care a great deal about consistency. MySQL does all of these really well, and in fact, MySQL servers can almost effortlessly reach 1 million queries per second. In fact, in benchmarks, they can do far more than this, but MySQL is very, very fast at these short queries. What it's not so good at is what we call analytic queries. And this is where we're dealing with data that is very large in the sense that you could have a huge fact table, for example, of instrument ratings or web logs or something like that. It could be very wide. This airline data, as we see, actually has 109 columns. You could be asking open-ended questions where you don't necessarily have an index. You could be asking questions about any of the columns in the table. And finally, analytic queries often have aggregates. So we're totting up flights by day or airlines by flights by tail number of the aircraft or by location, by how late they are. So many types of sums and other types of aggregates. And MySQL actually handles these relatively poorly, particularly as the data size gets a lot larger. So, if MySQL doesn't do so well on this, how does a data warehouse do better? So what we're going to do in this next section is I'm going to dig into a sample data warehouse, and in this case I've chosen ClickHouse as an example that we can contrast with MySQL, and we're going to dig into the plumbing of ClickHouse and see exactly how it handles some of these problems with analytic queries. So let's first look at some of the key features. In the same way that we surveyed them with MySQL, let's go ahead and survey the key features of ClickHouse. Well, the first two are the same. ClickHouse has a single C++ binary, so you just start it and you've got a data warehouse running. It also speaks SQL language. The dialect is superficially similar to MySQL, but as you get more deeply into it, it of course has major differences. The first place where we really find that things are different is it stores data in columns. So that's roughly shown here in these diagrams. The idea is that every column you can think of as being stored in an array. And what that means is as we read them, we're going to be doing sequential operations, either sequential reads or sequential writes. It has a number of other consequences, which we'll look at as we go on. Another thing about ClickHouse is it has very good compression. And it uses something called Codecs, which are an extension to compression, which can make the data very small. It uses something called vectorized query execution. So it's able to, when we get a query, ClickHouse will break it up, assign the parts of the query to multiple threads, and have them all attacking the data in a parallel fashion. That parallelization extends across nodes. So if you can't handle a query on a single node, you can actually, ClickHouse has built-in sharding and replication, which allow you to spread the data out and take advantage of the power of multiple servers. And finally, it's open source. It has an Apache 2.0 license, which is really very flexible. You can do practically anything about it as long as you include the notices in the code. So that's an overview of ClickHouse. What I'd like to do is just introduce a table definition. So we didn't show SQL to keep things short, we didn't show SQL for MySQL up above, but we're going to show it here for ClickHouse because it's a little bit different for people who have used MySQL. You see a create table definition, and we're creating a table called ONTime in database airline. One of the things you'll notice is the data types are a little bit different. So for example, uint16, uint8, these are ints, and similar to the SQL data types, you can actually map them mentally. We have the flight date, which is a date. We have string, which is of course, a string, and or actually varchar to put it in, or char to put it in MySQL terms. What is interesting, though, is there are a couple places where the definition is quite different. First of all, we have this thing called engine equals merge tree. So in MySQL, we're used to things like engine equal myISAM or engine equal InnoDB. This merge tree engine is saying, hey, I want to store the data in columns, and this is a very high performance table that's used for large amounts of data. There's a partitioning key, which tells us how to break the table up into pieces so that we know how to process it efficiently. And then there's an order by, and we'll see what these mean in just a second. There's another important thing, which we see the special syntax for the columns. For example, codec. What that means is that we're able to specify the compression process that occurs when the data is stored. There's another thing we see here called low cardinality. That's a special type that's applied to strings that allows them to have dictionary encoding. We're going to dig into those in just a second because they're very important for ClickHouse performance. The final thing to notice about this is if you have in your heads the third normal form we just saw, what this definition is already doing is it's starting to pull two of the three extra tables into ClickHouse. So that's a third difference, and we'll explore why that's also important. So let's first look under the covers at the organization of the tables. So as I said before, ClickHouse is a column store. So we're organizing things basically in arrays. And if you look inside one of these parts, which often consists of 50 million rows or more, this is a chunk of the table which contains an index. So that is what we call a sparse index. It allows us to refer to find, quickly scan and find the particular values in the table that are in what we call the primary key or the sort order, which are basically the same thing in ClickHouse. And then for each column, there's a pair of arrays which represent, first of all, the offsets for the rows into the column so that we can find the right position for a particular row in the column. And then the second of the files is just compressed blocks of data. And in fact, there's an illustration with the sparse index. When you read the sparse index, for example, if you're looking for a flight by carrier, you'll find the carrier and you'll see a bunch of you'll get a range of data that you need to read for that carrier, and then you'll go read the range from each of the rows you've selected. So that's basically how this works. There's a big difference, though, already in not only the columns, but also the way the indexing works. The index is basically just an array. It's a linear search, and it is a sparse index. It's very small. It actually only records values for every 8,000 or so rows by default, and it's done that way so that it can fit in memory. Let's go have a look, though, at what this then does when we store data in it. Well, a big consequence of this organization is there's no longer a penalty for having wide tables. This graph here shows you the exact amount of storage that's used for each of the 109 columns in this airline database that I'm using. It has 173 million rows in it, and the orange bars show the uncompressed size of the data in each column. So the smallest columns are on the left, the largest columns by size of data are on the right. So what this means is if you have a select and you have to do a table scan, and you are only working on 3 columns, you will only read the data for those columns and no others. What that means is if you pick a couple of the 3 of the middle columns, you're only scanning a few percent of the data. So you've vastly reduced the amount of data you have to read. Now, ClickHouse goes one better on this because not only is the data segregated by column, but within each column it's compressed. So the blue bars show the actual amount of data that's present in these columns in storage. And as you can see, because of compression and the fact that some of the columns are just empty, there's a much smaller amount of data actually out on your storage devices. So even if you touch the column, you may read vastly less than the uncompressed data size. And in fact, for this particular example, the data is compressed by about 75%. That's something that we did without doing a great deal of extra work. Let me show you a little bit about how compression works, because this is really important to understanding how ClickHouse can be so quick. So we're not going to be reading the columns if we don't refer to them. Within the columns that we do refer to, there is a process that we follow that determines how much storage we're going to use. So the first thing is picking the data type correctly. The second thing is to apply 0 or more codecs. A codec is a type-specific transformation that reduces the input data size to the last stage, which is compression. And ClickHouse supports LZ4 and ZSTD compression. LZ4 is the out-of-the-box compression. It's pretty quick. Doesn't quite compress as much as ZSTD, which has differing levels, higher CPU costs, but much better compression in some cases. So here's an example of choosing a data type. We use the low cardinality data type on string. That turns strings, for example, airport names, into a dictionary encoding. So instead of storing the full name of the airport, we're just going to store an integer. In this particular example, there's no codec applied, and then we have LZ4 compression. Another example, we have an unsigned int 32, so an int. We apply double delta codec, and what that means is instead of storing the integer values, we're going to store the slope of the integer values. So if it's an ascending value like time or something like that, this can be very efficient. We only store a few bits for each column or for each row value. And then finally we apply ZSTD on it. The effect of this can be really spectacular and is one of the big things that ClickHouse does very well. This graph shows you some of the effects of the column sizes of this compression. So the light blue bars are the uncompressed sizes of columns. They're measured in megabytes. So for example, we have carrier, which is one of our fields. It's just using out-of-the-box LZ4 compression, and we get down to 5.64% of the original data size. But we can do better than that by tweaking it and actually explicitly choosing the low cardinality on string, so the dictionary encoding, and then still using out-of-the-box LZ4 compression. We now reduce that to 0.64%. So this data size for this column has been reduced by a factor of over 100. We can do similar things on flight dates. So we see flight date with LZ4, contrasted with double delta and STD. And then on the right side, what we see is not everybody is perfect. The origin is an airport code. In this particular case, we haven't applied a codec to it, and it compresses to 48% of its original value. So that's about half the original size. We can, of course, tweak that and make it much faster. So, or make it much less. So reducing the size of data is critical because one of the fundamental driver in analytic queries is I/O. So the less you do of it, the faster you're going to go. Now, given that you've reduced things to some reasonable size, then what you can do is throw CPU at it. And one of the other things that ClickHouse does, and analytic databases in general do very well, is they utilize hardware resources to parallelize query, to get parallel query. So here we have the example that we're using right here. We're looking for canceled and delayed flights. And what we see is that if we use 2 threads, which is 2 hardware threads, to run the query, it runs in 0.884 seconds. It's about half that if we double it. As we add more threads, it asymptotically goes down, but it doesn't increase as much. Part of the reason is that there are some things that are single-threaded here, like grouping and sorting. Also, I'm actually running on a machine which is 4 cores and with hardware hyperthreading enabled. So in fact, there may be some blocking on the cores as it goes to higher numbers. But the basic idea is that if you have the CPUs and give them to ClickHouse, it will use them, which means your query goes that much faster. If that's still not enough, you can actually pre-aggregate data using materialized views. So materialized views basically is like a trigger. It works on a source table. Every time a block of data lands there, it's run through the materialized view and then transformed into values that get stuck in the target table. In ClickHouse, this can be used in many ways, but one common way to do it is through aggregates. So here's an example where this slide is a little bit crowded, but I've created a materialized view which basically pre-aggregates the information required to answer that canceled and late query I showed just a minute ago. So you can see it's a relatively simple definition. It's transformed by a select, and what it does is it reduces the size of data that we have to scan from something like 14.59 gigabytes down to 2.31 megabytes. So it's an enormous reduction in the data size that will be examined to when we're answering these questions. And the practical result is you get a query speed up of on the order of 50 to 100x. It's even bigger if you have larger data sets. So this is another thing that ClickHouse does that is very, very helpful. And since analytic queries tend to have a lot of aggregates, it means that you can get enormous speed increases. Beyond that, if a single host won't do the job, you can add more servers. And this is a final area where there are significant advantages in a data warehouse for analytic queries. So with ClickHouse, you have built-in replication. That helps you with concurrency because you have multiple copies of the data. It's like selecting on MySQL replicas, except that it's just built into the database. And you also have sharding, so the ability to split a data set up into disjoint parts and then have a query automatically dispatched to all of the parts, run the subquery, and then the results are assembled back up. So that increases your read and write bandwidth. And here's a simple example of the sort of increases in performance that you can expect from that. So this was a more complex query running over the 173 million rows. I had relatively low-powered hosts on this, but you see basically linear performance as we go from a single shard to 2 shards to 4 shards, both cold runs where we're going to forcing everything to go to storage, and then hot runs where we're coming out of cache. It's linear in both cases. So this is another way that you can, if you have data sets that are scaling out to trillions of rows, ClickHouse can handle this very effectively through clustering. So coming back, we can look at the strengths and weaknesses of ClickHouse. And what's interesting is if you're deciding between MySQL and ClickHouse, in some ways the strengths of ClickHouse are a mirror image of the MySQL weaknesses. So the structuring of the storage, the ability to do compression, the ability to parallelize queries both across individual CPUs and single hosts, as well as across many hosts, mean that you have very high performance for things like very long tables, very wide tables, where you ask open-ended questions for which there's no available index and you just have to do a brute force scan, and any application that computes a lot of aggregates. On the other side, the things that MySQL does well, ClickHouse does not do particularly well. So for example, if you have lots of tiny lookups, ClickHouse will by default read 8,000 rows at a time in the columns that it's selecting. Updates are slow because you have to update files across all these columns. High concurrency, ClickHouse is not really designed for it. Moreover, if you use hardware efficiently and give it to one query, that means other queries cannot run at the same time because there's no CPU available. ClickHouse is it will consume all the resources that it's given. And ClickHouse uses a loose consistency model, for example, on the replication, which is eventual consistency multi-master replication. So if you're running a bank, ClickHouse is probably not the right database for you. But on analytical applications, ClickHouse can be vastly faster. So, and by vastly, I mean faster by 1,000 times or more. It's an enormous performance difference. Okay, so let's wrap this up. You have sort of the basic, we had the introduction to MySQL, we had the introduction to ClickHouse, and we dug into some of the plumbing. Let's take it up a level and just talk about specifically in terms of applications. So MySQL, once again, it really shines for things like transaction processing. And if you run a website, you've probably seen this screen. This is WordPress. This is the application, that sort of the killer app for MySQL. It has a huge number of tables, lots of things linked to each other. You may have many people accessing at once, getting small amounts of data to feed pages. MySQL is wonderful for this. This is what it was built for and is still one of the cases where MySQL is a great solution. ClickHouse, on the other hand, is great for analytic apps. If you run a website, you've probably also seen this one. This is Google Analytics. It doesn't have ClickHouse underneath it, but as it turns out, ClickHouse was actually written for Yandex Metrica, which is exactly the same sort of application, just running at Yandex. So in this case, we have large numbers of very large queries over vast amounts of data, lots of aggregates, complex conditions that require table scans. ClickHouse is great for this. It does lead to a question, a final question. Is there a single database that can handle both of these? And the answer is, so far, not really. And there are a lot of reasons why this is the case, but I think there are two that I would point to. As you've seen even from this talk, we didn't go that far in, but you can see that there are basic differences in how you tweak the underlying storage, how you configure things, and these are all decisions that are made by app developers typically, that are not made automatically, that are necessary to get decent performance at the database level. So that's one reason. If you try to put these two things together, it makes the database very complex. The second thing is, think at the app level, would you want to have WordPress combined with Google Analytics? That's a very complex app. In fact, people tend to divide and conquer and build independent services that do different types of things. And for that reason, the market really isn't asking for, in my opinion, really isn't asking for databases that can do both of these things equally well. Okay, that's it. So quick conclusions. Row stores, as we saw, like MySQL, great for transaction processing with lots of updates and small queries and high transactional integrity. Column stores like ClickHouse, they're great for analytic queries. Wide, long tables, open-ended questions, lots of aggregated results. So I would say look at your application. Which of these do you have? If it fits into one of these two buckets, probably have a pretty obvious choice on your database. And with that, I'd like to say thank you. It's been a pleasure doing this talk. Thanks again to Percona. Visit us at altinity.com, and here are the links for my email if you have further questions, as well as links to the ClickHouse code and MySQL. If you need to find out about MySQL, you can't go to a better company than Percona. So have at it, and I hope to answer your questions. Thank you, and bye-bye.